This is the Earth Science Classroom. Welcome back. This video is on stress in the Earth's interior, more particularly the lithosphere and the asthenosphere and also the crust, how it's deformed, how we get our earthquakes and our volcanoes and generally our plate tectonic theory, but looking at the stress and the transfer of stress from the Earth's interior to the surface. Let's look at stress. Now, stress is force applied to an area. And we can also discuss stress in regards to energy, right? The transfer of energy. Because energy can be transferred and not destroyed. Here's our stress. And the stress is going to present itself as deformation in the crustal rocks. So, we're looking at earthquakes. And we're looking at plate tectonics as an over-encompassing theory that controls all of these surface features and surface tectonic expressions that are the result of underlining Earth's interior mechanisms and processes. So we're seeing the effect of the convection currents materialize on the surface as subduction zones, as trenches, as volcanic regions or zones, and also as these plate boundary earthquakes that occur. Now, 90% of earthquakes occur on plate boundaries, and they kind of give us an idea of where these boundaries are based on their location and also their depth. So the size and the depth of the foci of that earthquake or the earthquakes gives us a sense of, how much energy and therefore how much stress is being not inputted but kind of added to the rocks in the first place. And where's that come from? So take a quick gander at the Earth's interior. And I have a lot more different videos on these layers and on these different zones and Earth interior sections if you want to check them out. They're in the Earth's interior playlist. The upper mantle is where all of the transfer really is understandable from a student's point of view. Now, if you want to get into higher level geophysics and geochemistry and how the Earth's interior works, that's fine. But for my classroom in particular, with a high school classroom, you want to bridge that gap. You want to bridge the gap from middle school science, which is very introductory and very just brushes over large concepts, doesn't really get into much detail, and obviously the college or university level, which is going to obviously be a higher level of content and a higher level of rigor when it comes to these scientific disciplines. But you want to bridge the gap, and you want to explain to the students that there is this low viscous or low viscosity zone or layer, and obviously includes the LVZ, which is low velocity zone, again based on seismic waves and how they travel through different speeds based on the composition, density, and medium that they're going through. So we have the asthenosphere, lithosphere, and crust. So this really is the upper mantle, starting from the asthenosphere up to the surface and the crust. Now, technically, the crust is a part of the lithosphere, and you have the moho here, which is dividing, which is right here, a little dashed line right here, that's dividing the crust from the increased density layer of lithosphere. And lithosphere is kind of a uniform composition, and the crust, obviously, we know can fluctuate between basaltic, which is more oceanic, to our granitic and andesitic, which is our continental. But what we have here inside the asthenosphere is a very slow motion, very consistent movement of heat and plastic material that we know as a convection current. Now, it's moving heat generally from the deeper regions, which is hotter, to the shallower regions, which is going to be colder. But heat is obviously thermal energy. So we have our energy and where it really comes from. And the energy is then transferred into this lithosphere, which is a solid layer. Now, it does get kind of hotter at this depths of around over 25 kilometers. It gets to be around 300 degrees Celsius. Now, it does become more ductile and more able to bend and move more so than if you go actually towards the crust. You go anything between obviously 0, which is the surface, to 25 kilometers. This area, this depth under the surface and at the surface is going to be increasingly brittle, which means that any stress that's added to the rock, there's a certain limit or a point of failure where that rock is not going to bend or just be elastic and snap back into place. It's going to break. It's going to cause fractures and joints, and in this case very large fractures and very large divisions that we call plate boundaries. And these plates, both major and minor and micro, are going to be created on the Earth's surface, and because the stress, the heat energy is transferred into the lithosphere and the stress builds up, you get the formation of these plate boundaries and these plates. We established that the convection currents, put Cc, are going to add heat energy into the lithosphere at the bottom, and this transfer of energy will continue to build up inside the lithospheric rocks. Now, depending on the rock's type, which is generally ultramafic at that depths, and you might get some obviously silicate minerals, obviously that's the main composition of the crust lithosphere, you're going to get a certain amount of energy being stored. So this energy is stored, a massive battery, inside the rocks. So as a review of the stress types, well, you obviously have gravity as a consistent force or constant force. You also have lithostatic pressure. It's very similar to hydrostatic pressure, but this is lithostatic pressure, which means rock. Lithic is a word for rock. So there's definitely going to be pressure created by gravity, and also the mass or the weight of the overlying rock, or the overburden that's going to be pushing down through gravity, creating this constant pressure. So what we get is these different types of pressures and stresses. So what we have is our three types of stress, which is compressional, tensional, and shearing. Now there is a fourth one which can be discussed as confining stress, but that really is the similar way to lithostatic stress, whereby the piece of rock, I'm just using a rock block for example, is experiencing pressure and force applied from all angles and directions. In this case, as a uniform pressure. So there's no one area, one side that's higher than the other. This would be if you do get a area that is experiencing higher levels of different directions of stress being applied to that rock, then you would look at, is it going to squeeze in towards, which is compressional, is it going to be pulling or extensional, that's tensional, or is it going to be opposite directions, which is shearing. So these three are the main ones that really create those fault lines and the breaks in the rock, which then lead to earthquakes. But you have to understand that this stress is coming from the convection currents and the movements. When you start to move plates, right, the tectonic plates are being moved by these convection currents. They are moving very slowly across the surface of a three-dimensional sphere, and these plates are in excess of millions or billions of tons of rock and material that you're going to get the frictional stress built up as well, and you're just going to have rock that cannot handle the energy and the movement, and it's going to naturally fracture. Plus you have to add in the convection currents are going to provide rising magma, which would also create movement and stress and energy applied into the rock, both heat and force. So this video is looking at how to bridge the educational gap between the Earth's interior layers, convection currents in the asthenosphere, and the expression of plate tectonics on the surface in or resulting in surface features, geomorphology, and tectonic features that occur as a response to what's going on beneath the feet, beneath the crust. Things like the volcanoes and the earthquakes and trenches, subduction zones, orogeny and mountain ranges, and different basins and ranges, all as a consequence of these large plates moving because of stress and the convection currents. And the stress builds up in between these rocks and is released as earthquakes pretty much every day. Some small earthquakes pretty much every day, to larger earthquakes maybe once a month or once a year. But to understand these stresses, we have to look at what's called a principal stress. That is the main stress that's causing the force and causing the movement. Because in earthquakes and in fault lines, you have one side or one aspect is going to be moving and releasing the energy that's been trapped in the rock that we discussed of how that energy gets into the rock in the first place. And this obviously results in an earthquake. But you have an idea of which side's moving and where the stress is coming from to create that movement of the rock. And don't forget, this is very brittle. So you add the stress, you're going to have a lot of breaking of rock. You're going to have a lot of joints. You're going to have a lot of just fractures and fracture zones. And in this case, you're going to have a lot of faults. So Anderson, in 1951, came up with an idea, pretty much added in a lot of math, understandings, to take an earthquake and figure out where the stress came from and to use a model, a beach ball model, to highlight and demonstrate those stresses. And he classified them according to the types of faults. So he had this idea that if you have a rock, a simple rock, it's exposed to or is under the influence of both vertical and horizontal stresses. And he classified them like this in a three-dimensional model. So there are three stresses. There was, or sigma 1, sigma 2, and sigma 3. Now, there was a maximum stress, which is one that's causing the movement. So you can ID that one. There was a minimum stress. That was just there. It was present. And there was an intermediate stress. Now, these three come in different orders. And the different orders and the different types of stress would correspond to a certain fault or fault type. Don't forget the fault type, we're looking at a dip, slip, both normal and reversed. And we're looking also at a strike slip, which is that horizontal displacement. You can also look at oblique fault, which is a combination of the two, but we have the three types right there: normal, reverse, or thrust, and strike slip. This is the Earth Science Classroom. Thank you for watching. I hope you enjoyed the content. Check out more videos on our channel, and don't forget to subscribe. Thank you again.